Today we're going to be looking at example 7, and this is in lesson 13, sketching gradient functions. This exercise is quite long, this lesson's quite long, so we've sort of broken it into 2 lessons, but yeah, so we're looking at example 7, so sketching graphs without the assistance of a graphical display calculator. So for the functions y is equal to, if the function y is equal to x cubed plus 3x squared, take 24x plus 20 without the assistance of a calculator to determine A, the coordinates of the y-intercept. Well, we know we can find that if we make x is equal to 0, y would be 20. So that's not too bad. The behavior of the function as x goes to positive infinity and negative infinity. So where is y tending to? Now we know that this function is a positive cubic, so we know it's going to look something like this. Okay, that x cubed term is going to dominate, and when, say if we put in x as 1,000 cubed is going to get very, very large. So we can say that as x approaches infinity, y approaches infinity, and because it's an odd function, as x approaches negative infinity, y is approaching negative infinity. Okay, so we've done that there. Let's go on to C, the location and nature of any turning points. What we're going to do here is we want to work out this turning point and that turning point there. We can use our graph, but I also want to double check using our double div test. Okay, so here we go. First thing, turning point. We know a turning point's either only a min or a max. Okay, and we know dy by dx at this point is 0. So we've got to differentiate. Y is equal to x cubed plus 3x squared minus 24x plus 20. Dy by dx is equal to 3x squared plus 6x, take 24, make it equal 0 because we're looking for a turning point. Can we simplify this? Unfortunately, it looks like we can take out, we can take out a factor of 3 there, so we can make it monic, which is always nice. Then we can cross out that 3. Okay, now let's factorize. It's going to be x, was it plus 4, x take 2. So we've got our solutions. X is going to be negative 4 and 2. So what we've found here is that this is going to be 4 something, and this one, this is going to be negative 4 something, and this one's going to be 2 something. Okay, so we've found those turning point x values. Okay, now we want to let's just find those coordinates. So finding those coordinates. When x is equal to negative 4, put it into our function. Okay, and y will pop out to be 100, and then we can put in the other one. X is equal to 2, plug it in, and y comes out to be negative 8. Okay, so now we've got both our coordinates. We've got this coordinate here, which turns out to be negative 4, 100, and this coordinate here, which turns out to be 2, negative 8. So we can put that in there. Okay, now we've got our where our turning points are. We now need to check their nature. Okay, so here we go. Let's find the nature of these points. So nature, first thing, d squared dx squared, and we know if this is positive, then it's going to be a min, and if it's negative, it's going to be a max. Okay, so let's investigate both our turning points. So differentiate again, 6x plus 6. Okay, so that's our double diff function, and then we're going to plug in our x values. So our first one was when x is equal to negative 4. Let's see the nature of this here. If I plug that in, it's going to be 6 times negative 4 plus 6 which is negative 24 plus 6. So we can see that this is going to be negative. Therefore, this coordinate here is, and we can say as it's negative, it's a maximum. Let's just double check our graph. We can see that, yes indeed, that does look like a maximum. I'm just using a double diff to test that, okay? And let's test for the other one. X is equal to 2. Sub it in. Okay, we got 12 plus 6, which we can see is positive. Therefore, we can say this point here is going to be a min, okay? So we've got our nature using the double div test. We've found our turning points. We've seen now the location and nature of any turning points. Now, the next part here says the coordinates of any points for which the double derivative is equal to 0, okay? Now, let's have a think about what those values can be. Do you remember before we went through some of these examples, you may note if it's a min, you've got f dash x is 0, and then it goes positive, a max. We can say f dash x, the gradient is going to be 0 at that turning point, but then it's going to be negative as a double diff. Now, a horizontal point of inflection, we can see there, the double diff is going to be 0, okay? And same for vertical points of inflection as well, okay? So we're probably going to be finding an inflection point, okay? So let's double diff and let's figure out what we get. Okay, so let's go black. There we go, and D. Okay, and I'm just going to write a note. This is probably going to be an inflection point. All right, so let's differentiate once more. Okay, and we already know that we've already done that. 6x plus 6. We're going to make it equal to 0. Solve. X is equal to negative 1. So what we found here, that x is equal to negative 1. Okay. Now let's plug that into our original formula, that x is equal to negative 1. Okay. So y is equal to, and we've got this function up here. So negative 1 cubed plus 3 lots of negative 1 squared, take 24 lots of negative 1 plus 20, okay, and out comes 46. Okay, so now we have negative 1, 46. So let's put that into our graph and have a look. Negative 1, 46 is probably going to be around here. Okay, like that. All right, so negative 1, 46. Now, what point does that look like to you here? Well, we can say that this is probably going to be a vertical point of inflection. Do you remember vertical points of inflection? A VPI is where the gradient is the steepest in a region. Okay, so we can see here that at this point, if I drew a tangent, it's probably going to be the steepest there. So we found a VPI. Now, what do we know about VPIs? Let's go back to our chart here. Now, it looks like it's this kind of VPI. So it's saying that the gradient at this point is going to be the steepest negative, right? And we can see that the double diff is going to be 0. So we could confirm that if we wish. Okay, so looks like we found it's a vertical point of inflection, a VPI. Now, show your answers to the previous parts on a sketch the graph. Now, I've done this very rudimentary sketch in the graph here. If you want, you can clean that up. You know, I don't have too much space, but if I was to do this, I'll just do it over here. Now we can draw in that y-axis. It's quite hard to know where that y-axis goes. The x-axis is easy, but where the y-axis goes can be a little tricky, so I typically don't draw that in until the end. And let's just sort of draw in what we have. 2, 3. Okay, and let's say each one of these is 20, 20, 40, 60, 80, 100. negative 400. So we've got a point here. And this is our max, local max. We've got a VPI at negative 146, negative 120, 40, around here. Okay. We've got another point at 2, negative 8. What else we have? We had a y-intercept at 0.20. Okay, just there. And I think we've got enough to probably start sketching this thing. We don't have those x-intercepts, unfortunately. And this is just sort of ballpark, right? Now, if you had a grid or something like that, you might make a better attempt at that. And I'm just going to put those coordinates in. So our min. Here we've got our VPI, and that's at negative 146. And then here I've got my y-int, and that's at 0.20. And then we can write the function here. Y is equal to x cubed plus 3x squared, take 24x plus 20. So there we go, we've completed that question. What's really interesting about this is we're actually finding an inflection point, and they're not too bad to find inflection points. You just have to find when the double diff is equal to 0, instead of when finding a stationary point where the gradient's equal to 0. I hope you found this video useful. Thank you.